and all. This is Dr. Raja Chandrasekharan. I welcome you all to the session on weight regularization to address the model overfitting in machine learning. That is, when we train a supervised model, the model defines a function by mapping the inputs towards the targets or the labels of the corresponding inputs. So the model learns by modification of the weights when it maps the inputs towards the targets or labels. The model then evolves through the modification of weights, reducing the mean square error or improving the accuracy. That is, the supervised learning is nothing but an input is there, a target is there, and the label of the input or target is there. The model learns by defining a function that maps the inputs towards the target, and the weights are modified iteratively towards the direction in which the mean square error is minimized or the accuracy is improved. But what happens actually? So with a limited set of inputs in the training session, what happens is the model overfits. That is, the weight gets elaborately increased so that it is fit only for the data or input that is available in the training set alone, whereas it fails to fit any of the new data. That is, it overfits. It particularly matches only to the training set of data. It fails to map to any other set of data. So we can compare this behavior with the human beings also. So we overfit to a certain environment, so we may be becoming unfit to any other environment. That is what is called as the overfitting. Overfitting is nothing but it adjusts much more towards a particular set of training data when a new set of data that is not there in the training set, when that is given to the input to perform, or it is not able to classify it properly. So that is because of the weights becoming too big and the model fails to generalize. That is, it misclassifies the input that are not from the training set. Hence, we need to address the weight growing. So weight growing in certain directions, at least we have to limit the capacity of the model. So if we inhibit the weights in certain dimension, that is nothing but reducing the capacity of the model itself. So going in depth, so people who are all very clear about the model generalization, overfitting and underfitting and all, they can directly go for the L2 penalty, which comes in a later session of the lecture. We can forward and see. Now we will elaborately discuss from the basics what is meant by a training and testing example, what is underfitting and what is overfitting, why there is generally a overfitting in the machine learning or deep learning model. But particularly when deep learning has evolved, there is too much of features extracted from the input, so a model is certainly subjected to overfitting. So let us revisit to training and testing examples. What is meant by testing phase? In testing phase, we have set x of m example inputs that we will not use for the training, use only for the testing. That is called as the test data set. We also have a vector of targets for the test data set. So the labels for the inputs that are there in the test data set, that is also there. So we have a vector of targets providing the class of y for each of these inputs. So that is called as a test data set. Testing involves prediction of y, prediction of the class of y actually. So the prediction, we call it as a y cap for each of the inputs. So we will start calling this as x test and y test. So x test is nothing but the input in the testing phase, and y test is nothing but the labels in the testing phase. And what is y cap is nothing but the value that is predicted. So y is nothing but the actual value and y cap is nothing but the predicted value by the model. And to measure the performance of the model, we usually compute the mean square error of each of the model on each of the test set. So the mean square error is given by y cap test, that is the value that is predicted by the model. That is, it belongs to class 1 or class 0 that is being predicted by the model, and whatever class it actually belongs. So for each of the input I, so I is equal to 1 to m and dividing by m, averaging out the number of cases, we calculate the mean square error. So a machine learning model is typically has the intention to reduce the mean square error. And generalization in machine learning. The ability to perform well on previously unobserved inputs is called as the generalization. Generalization error is defined as the expected value of error to a new input. The factors determining how well a machine learning algorithm performs, defined by making the training error small. The training error should be reduced. That is obvious. That is a very primal condition. And making the gap between the training error and testing error small. This is what we are going to address in the concept of weight regularization. These two factors correspond to two central challenges in machine learning, that is underfitting and overfitting. Underfitting occurs means that the machine learning algorithm is not eligible at all. So underfitting occurs when the machine learning algorithm is not able to sufficiently lower the error value on the training set itself. So then you have to increase the capacity. Maybe the capacity of the model is not suitable for the inputs you are giving. So here what is meant by the capacity? Capacity is nothing but the order of the hypothesis space. with which the algorithm learns. What is by the order of the hypothesis? So we told that the weights are changing. So in what is the learning? In what hypothesis space it is learning? Whether it is a first degree equation or second degree equation or third degree equation. Overfitting occurs when the gap between the training error and the test error is too large. We can control a model is more likely to overfit or underfit by altering its capacity. That is, when the model is underfit, we have to increase the capacity of the model. That is, if the input deserves to be learned at a higher order hypothesis space. That is, if it requires a order 9 equation, when we are giving for only for a order 2 equation, the hypothesis space to learn is very less. So you have to increase the capacity of the model. Whereas on the other way, if the input that is to be learned is a very linear set of inputs that can be classified by a linear equation, and you are going for a very high non-linear equation, means the capacity is very high mapped to the input. So then what happens is overfitting happens. So it may not be able to classify a new data. So that is what we are going to discuss in the entire slide. Models with low capacity may struggle to fit the training set. Models with high capacity can overfit. One way to control the capacity of a learning algorithm is by choosing the appropriate hypothesis space. So what happens when you increase the capacity of the model? So here the x-axis is capacity. So don't mistake it as iterations. So normally people who work with machine learning, they may think this as the iteration with respect to error. This is what we usually do. Theoretically this is little different. This is the capacity of the model. So the solid lines, that is nothing but the testing, and this is nothing but the training error and testing error. So testing error is what we relate to generalization also. So in the training phase, what happens, if you see, when the model capacity is very less, then here also the error is very high. So when you increase the capacity of the model, the error becomes convincingly low and the error keeps on reducing. So this is what is in the what happens in the training phase, but this doesn't happen in the testing phase. When you keep on increasing the model, what happens is, when you give the new set of inputs, what happens is the error becomes more. That is, it fails with the new set of inputs. So this is what is called as a generalization gap. Regularization again. Regularization is any strategy we adopt to a learning algorithm to reduce its generalization error. That is, to make a machine learning algorithm capable of accepting new inputs and classifying them also. That is what is called as a generalization. To go for generalization, whatever strategy we adopt is called as a regularization. So what are the different strategies and what is the most popular thing if you ask? That is weight decay. The capacity or the hypothesis space should be limited. What is that? Is nothing but so what is that hypothesis space? The order of learning that is allotted for a machine learning algorithm. Suppose if you are giving an input, linearly separable input, and you are having a highly non-linear learning algorithm. So then that is too much to learn that input. So what happens is overfitting happens. So likewise, one way of doing so is by reducing the weights in select dimensions. I am giving it very carefully because we are going to arrive at this only. In select dimensions, the weight are being often the weights to be learnt in other dimensions. So what is happening is the capacity of the model is restricted in such a way, which is called as a weight decay. So weight decay in the sense not all dimensions of the weights are reduced. In select dimensions, we are nullifying the learning. It reduces the capacity of the model. To what dimension it is learning, that is being restricted to limit the capacity to avoid overfitting. So, and one of the regularization strategies is a weight decay. Coming to the formula, so j of omega. So j of omega is the objective function that has to be minimized. So the objective function has two criteria, that is minimization of the mean square error. So let us assume that this objective function should be reduced. That we want to minimize this objective function, the mean square error should be reduced, that it has to be fit to the training data. And this term also has to be reduced. So what happens is the single objective function tries to fit the training data and also to keep the weights as low as possible. This is what is called as the weight regularization as of now. So the objective is to minimize omega, j of omega. The weights tend to fit the training data and also maintain themselves small. So what is lambda here is nothing but the hyperparameter. So what is our interest shown towards the weight regularization or weight decay? That is given by lambda. So if lambda is equal to 0, there is no weight regularization at all. So classical regularization or parameter norm penalty. So coming to the main topic now. So what is a classic regularization mean? Most classical regularization approaches limit the capacity of the model. So we are always talking about limiting the capacity of the model from getting overtrained to a certain type of data. Limiting the capacity of the model by adding a parameter norm penalty omega of theta. So whatever we discussed here, by adding a parameter norm penalty. So this is a penalty term here. In a more generalized way, it is given here as omega of theta to the objective function j. So final equation is here. So where j is the unregularized objective function, and j cap is after regularization of the objective function, and theta is the weight. So here we have to remember that theta is the weight and x is the input and y is the target, and alpha is a hyperparameter that we have already seen. So this is what is called as a L2 norm penalty. What is that L2 norm penalty? Is nothing but the norm square of the weight is added with the unregularized objective function. So norm square of the weight. So here omega of theta is simply the penalty term. So the penalty term is nothing but half of W square. W square is nothing but the norm of weight square. Theta is a parameter for regularization in the sense that is what it has to be reduced. Like here it is nothing but the weights. So there are some mathematical preliminaries to be understood for L2 parameter regularization. Familiar about the linear and quadratic approximations. What is the linear and quadratic approximations? After that, what is the Taylor series and what is the Hessian matrix and what is the eigenvectors and all we are going to see. So these are all the mathematical preliminaries that have to be learned to understand about the L2 norm parameter regularization. So what is linear and quadratic approximations? So consider a function f of x that is differentiable at a point A. So a function f of x is being imagined. That function f of x is differentiable at a point A. That point A we should select is, it is a tangential point. It is differentiable at the tangential point. The linear approximation of f is given by, this is the approximation of the given f of x. What is that approximation? Let us see. We will be able to find out the approximate value of f of x. Suppose f of x is a very complex equation. So that f of x can be simplified by using this linear approximation. F of a is a point, tangential point, f of a plus differentiation of f of a into x minus a. Likewise, you can keep on adding the terms so that linear will become quadratic. If second order is there, that is called as the quadratic approximation. So what is this? Let us understand first. So now let us consider a graph of function f of x is equal to 1 by x. So this is the function f of x is equal to 1 by x, which looks like this, and you have a tangent here which intersects at approximately at 2. So the tangent passes and we can find out the value near to 2. So what is given? F of x is equal to 1 by x is given. So as per the formula, we need to find out f of x is equal to f of a plus f dash of a. So finding out f of x from that f dash of x. So f of x is equal to 1 by x in the sense f dash of x will be equal to minus 1 by x square. Then y is equal to the f of a plus f dash of a. So f of a means 1 by a plus f dash of a minus 1 by a square into x minus a. So using this approximation, if you want to find out the value at x is equal to 2.1, in this equation just simply substitute for x is equal to 2.1 and a is already equal to 2, and we can arrive at an approximate answer 0.475. So this is called as a linear approximation. Whereas what is the actual value? The actual function being 1 by x. So if you want to find out at a is equal to 2.1, so 1 by 2.1 will be equal to 0.476. So we have almost approximated. So what is the use of this? So here the function is very simple. We may be dealing in mathematics very complex functions where we can have a very simple formula like this for a linear approximation. Only close to the tangential point. Another thing is, we want to find out the value near 10. That is not possible by this linear approximation. And what is quadratic approximation? Quadratic approximation is a second order approximation. It provides a better approximation to match the concavity of a point. So it better deals with the concavities and all. Generalizing, we are generalizing this linear approximation, quadratic approximation by means of Taylor's series. What a Taylor's series says is the approximation of a given function will be given by C0 plus C1. So you could have understood that C0 and C1 are nothing but your differential terms, whatever we saw here as f of a plus f dash of a. In the first, this is f of a, f dash of a divided by k factorial. That should be a k factorial. And also we need to know about the eigenvalues and Hessian matrix and all. So eigenvalues separately we will see, Hessian matrix we will see separately, and how we will combine both, that also we will see. And then we can directly go to the L2 penalty. So eigenvectors are the primary directions along which a linear transformation is done. So if some linear transformation like scaling or compressing is done, in which direction that particular transformation is done, that is given by the eigenvectors. So eigenvectors are the primary directions along which the transformations acts simply by stretching, compressing or flipping. So that is called as the eigenvector, which gives a direction, primary direction of a transformation. And what are the eigenvalues? Eigenvalues are nothing but the scale that is being done. Suppose if you are doing stretching, at what scale it is being stretched, that is called as the eigenvalue. Eigenvalue gives you the factors by which the compression or stretching occurs. So let us take some more insight. That is nothing but let us consider a matrix A for which the eigenvector is B. How to find out the eigenvector in the case for a matrix is given means that matrix is multiplied by a plus lambda I and all. To find out the eigenvector, there is a separate procedure that you will be knowing. So a matrix A is there, eigenvector is found out and eigenvalue is also found out as lambda means. What is the simplicity we can see is A into the eigenvector will be equal to eigenvalue into eigenvector. So that is a very simple formula. For example, a matrix is there like this. The eigenvector is 1 by 4. So that is the direction in which the particular transformation is being done, and the eigenvalue is equal to lambda is equal to 6. In that case, A into V. So this is a matrix multiplied by the eigenvector, that will be equal to multiplying the eigenvector by the eigenvalue. This multiplication is more complicated than this multiplication, 1 by 4 into 6. So what is by Hessian matrix? So several things we have seen as mathematical preliminaries for finding out for understanding the L2 parameter regularization. Linear approximation we understood, and what is by Taylor series we understood. Taylor series is also approximating a function. And what is the eigenvector and the eigenvalues and all we have seen. And what is by a Hessian matrix? A Hessian matrix is nothing but a Hessian matrix of a two-dimensional matrix x comma y. A two-dimensional function x comma y will be equal to fxx, fxy and fyy. What are all these in the sense? It is a differentiation along the x direction and again along the x direction. So this is the second degree gradient of the particular function f of x comma y at a particular point. So whereas f double x means the gradient along the rows twice, that is equivalent to del square f divided by del x square. We may not always think in terms of differentiation. We can also think if it is a part of an image. The image is there, pixel 1, pixel 2, pixel 3 and all are there in the sense. Second degree gradient of a particular point will be equal to the difference of that particular point with the preceding and succeeding pixel. In that case you will be multiplying by 2. All these things if you want to know, you can study the digital image processing by Gonzalez. The topic is filtering in the spatial domain. So fxy in the sense x is along the rows and y is along the columns. So first find out the gradient along the row and then find out the gradient along the columns. Here both being x, we find out as del square f divided by del x square. So this is what a Hessian matrix gives. Hessian matrix gives the gradient along different directions. To consolidate, eigenvalues of Hessian matrix gives the measure of the gradient in that particular direction. What do you mean by gradient here? The gradient is nothing but the change of error with respect to weight. We keep on changing the weights, but with the change of weight, the error should get reduced. What we are going to do is, in certain dimensions of the weight, the gradient may not be significant. Gradient in the sense, the rate of change of error with respect to weight, that may not be significant. We are going to offset those dimensions of the weight, thereby controlling the capacity of the model. The model capacity is also controlled by offsetting some of the dimensions of the weights. I would say this is a takeaway of the discussion that we have done so far. That is, to consolidate, the eigenvalues of the Hessian matrix gives a measure of the gradient in the direction. So what is meant by gradient? Gradient is nothing but the rate of change of error with respect to weights. So when the weights are changing in an artificial neural network, the error should be reduced. That is the ultimate objective. So the eigenvalues of the Hessian matrix gives the significant direction in which the weights are changing with respect to errors. So those are the significant directions. So the eigenvalues are not significant, so that particular weight parameter can be neglected. So that is the ultimate objective we are going to disclose at the end of the derivation of the regularization parameter. So we denote the regularization objective function by j cap. This is what we already saw. J regularization parameter. J is the unregularized parameter and j cap is the regularized parameter. And alpha is a hyperparameter that shows our interest for regularization. And omega of theta is the penalty term that is used for regularization. So theta is a term that is nothing but the weights we are using here to regularize as input for regularization. So then L2 parameter regularization. What is it L2 parameter regularization? The regularization strategy, that is a weight decay, drives the parameters closer to the origin. That is, weight is decayed and taken towards 0, at least in some of the dimensions where the gradient is not significant, where the eigenvalues of the Hessian matrix is not significant. That is, a regularization term is added, that is half of W2 square, which is the objective function where W is nothing but the weights. For L2 regularization, let us consider a simple version of the same formula. So the same formula, j cap of omega is equal to j of omega we have taken. Instead of theta, we have taken omega here. J cap of omega is a regularized output and j of omega is the unregularized weight function. So this is the the penalty term that is being added, alpha divided by 2 into norm of w square or omega square. So j cap is the regularized objective function, that is what we already told. And what are the different steps we are going to do in this derivation? So j cap of omega we are going to declare. So j cap of omega with respect to j of omega we have already told. That is why I have given this as step 1. So step 1 is already completed. And then gradient of j cap of omega. So gradient of j cap of omega is nothing but the differentiation of j cap of omega. So in the next step we would differentiate this. And after that the optimal value of omega for j of omega. So whichever value of omega for which j of omega will be minimum, that is optimal omega. So that we are declaring as w star or omega star we are declaring here. So and then we are finding out del j of omega star. So this is the first 3 steps. So initial step is over. So after the gradient of j cap of omega. So when you differentiate this, gradient of j cap of omega means you are going to differentiate this. So of j cap of omega, put a differentiation here. So here also a differentiation, and when you differentiate this 2 comes here, 2 and 2 getting cancelled, alpha into norm of omega. So that is what is the second step. Second step is over, del j cap of omega. And third step I told the minimum value for del j of omega. So for del j of omega, w star be the optimal solution for j of omega, not for j cap of omega. That also voluntarily we are telling. So they should be within bracket. So that is a secondary information. W star be the minimum value or the optimal solution for j of omega. That means when you substitute omega star here, then del j of omega will be minimum or 0. So that is what we are going to hear. The derivative is 0 for the minimal point. So I hope you understand. So when you substitute omega star for this j of omega, so then j of omega becomes optimal. So that means del j of omega star should be equal to 0. So del j of omega will be equal to 0 when omega is equal to omega star. What is the fourth step? Fourth step, if you see, fourth and fifth step, it is nothing but consider a neighborhood point h for omega star. Already you have declared a optimal point for j of omega as omega star. A neighborhood point you are considering there, that is h. And from that you take the Taylor series representation and then finally derive del j of omega. So this is the fourth step, a little bit elaborative step, that is nothing but consider a neighborhood point h for omega star, and h is equal to omega minus omega star to omega star. So omega minus omega star is equal to h, and that h is the neighborhood point for omega star. When you take up the Taylor series for j of omega, which is the objective function without regularization. So the Taylor series is j of omega star plus h is equal to j of omega star. So you do the approximation, isn't it? X of t plus a, like derived the Taylor series before itself. So j of omega star plus h is equal to j of omega star plus h transpose del j of omega star. So what you do in the Taylor series is, after the first term, f of a will be the first term, the second term will be the or f dash of a, that is a differentiation. So here also you differentiate, that is multiplied with the a, and then next with a square. So this is your a and this is your a square. So h of h transpose, so h transpose h into h, and here you have to note that this h is nothing but the SEN matrix. So this del j of omega star, and this is f dash of a means this is f double dash of a, as I already told. So recall that del j of omega star is equal to 0, that we derived just now. Del j of omega star will be equal to 0. So that should be equal to 0 means the formula gets simplified. J of omega is equal to, so simultaneously what you are doing is omega star plus h will be equal to omega. So that also you are substituting. Omega star plus h is equal to omega, and h is equal to omega minus omega star, that also you are substituting. H is equal to omega minus omega star, you are substituting in 2 places. So j of omega is equal to j of omega cap plus half of omega minus omega star. So this is what is the derivation we have derived so far. And gradient of j of omega. So the fourth step is not over. So after that what you have to do, del j of omega you have to derive. So at the end of the Taylor series you are getting j of omega. So gradient of j of omega will be del j of omega. So that will be equal to del j of omega star. And what is this? Again you are differentiating here. So when you differentiate this, let us take as x square. This is x square means what will happen? It will become 2x, and 2 and 2 getting cancelled. So that will be equal to omega minus omega star alone. So this is what finally you have concluded. Del j of omega is equal to del j of omega star plus h of omega minus omega. And again gradient of j cap of omega. So finally anyhow we want the regularized term. So j cap of omega, gradient of the regularized term that we got in the beginning of the derivation, so that you are taking here. In that you are substituting for del j of omega from the previous step. From the previous step, del j of omega you have to substitute here. When you substitute that, it will come like this. And just now we already derived that del j of omega star is equal to 0, and already we substituted in one of the steps. Here itself I could have substituted that again equal to 0, making it simple. But anyhow we have taken it so far here up to here. So now you can make it equal to 0, and h of omega minus omega star plus alpha omega, that will be equal to del j cap of omega. So I think the fourth step is over. After the Taylor series, finding out del j of omega, the Taylor series is over. And the fifth step also we started. Del j cap of omega we derived. Anyhow we want the regularized term. So we have to convert this del j cap of omega to del j cap of omega cap. So what is it? Let us see. So let w cap be the optimal solution for j cap of omega. Initially itself we told w star is the optimal solution for j of omega, w cap is the optimal solution for j cap of omega. So finally we want to move from w star to w cap. So when you have to substitute here as w cap, and del j cap of w cap also will be equal to 0. Why? Because this is also an optimal solution. When it is an optimal solution, when you substitute the optimal value after finding the gradient, that should be equal to 0. So del j cap of omega cap. First of all, what is the del j cap of omega cap means? Here make all omega as omega cap. So h into omega cap minus omega star plus alpha into omega cap. So don't think this as a function. So this is always into multiplied by plus alpha into omega cap. That should be equal to 0, and making that entire thing equal to 0 here. And finally we want omega cap from omega star. So rearranging all the terms, there are several steps that are given here, which is, so taking omega cap on the other side, this is equal to h plus alpha I inverse into h into omega star. You may be knowing all the terms, you may be familiar with all the terms here. Omega star is the unregularized weight, and omega cap is the regularized weight, h is the SEN matrix, and alpha is the hyperparameter. So all these terms we are getting. It is unregularized objective function, unregularized weight w star becoming the regularized function, regularized weight w cap, and we have the SEN matrix h and alpha the hyperparameter. So the hyperparameter alpha is the interest towards the regularization. So when alpha is equal to 0, there is no regularization. So we can observe that omega cap will be equal to omega star. So by mathematically substituting alpha is equal to 0, that can be observed. And then when alpha is not equal to 0, there is a regularization, and then the Hessian matrix comes into the picture. The Hessian matrix is symmetric. Already we saw the eigenvector of the Hessian matrix should be taken. So the eigenvector will dictate the significant directions where the weight should be preserved. So that Hessian matrix H is split into the eigenvector Q and the diagonal matrix lambda. So lambda is a diagonal matrix and Q is the eigenvector. The eigenvectors of the Hessian matrix gives a measure of the gradient in that particular direction. That is, if the eigenvector value is higher, then that gradient is significant in that direction. So coming back to the same equation, and H is substituted by Q lambda Q transpose, substituted in both the places, and the same equation written here, and there is an entire lengthy derivation which involves very simple mathematics. So both the places we have substituted here. And here also you multiply with the Q transpose to maintain the commonality between the two terms. Q into Q transpose is going to be 1. So you multiply that here and take the Q and Q transpose commonly here, and that is this step. And after that what we are doing is we are putting the minus sign in the inverse inside. So it becomes Q inverse and the Q transpose inverse. So in the next step, Q transpose inverse is thought of like Q inverse transpose. So the transpose of the same term, so they are getting cancelled and becoming equal to 1. So the remaining terms are written here, and finally we are simply rearranging. When we rearrange, what happens? The Q is taken to this end, so that is being separated by the diagonal matrix lambda. So already initially when we taken in the last one, so eigenvector and diagonal matrix lambda. So finally also we separate this Q and the Q transpose, taking the diagonal matrix inside. So the entire term involving lambda is a diagonal matrix. So simply we write that as a D and call it as a diagonal matrix. And how the D will be looking like is taken here. So D is equal to lambda plus alpha inverse into lambda. So that is what, as per the last equation, it is the lambda is there in the entire numerator, and in the denominator you have lambda plus alpha I, and we have up to n. So n is the dimension of the weight vector. So as of now, leaving back this diagonal matrix and taking it for analysis later and coming to the entire part of the derivation. So now what we are going to say is the W star is the weight matrix and Q transpose is the eigenvector. So Q transpose is the eigenvector, is going to say the significant directions of the weight vector. So when a matrix hits a vector, what happens? When a matrix hits a vector, the vector is rotated and scaled. So imagine a weight vector or simply any vector 1 by 3 vector. If that vector 1 by 3 vector is multiplied by a 3 by 3 matrix, what happens is the values get changed. So when the values get changed, automatically it is shifting in direction. So the vector is shifting in direction when it is getting multiplied by a matrix. So weight matrix, that is W star, multiplied by the eigenvector Q transpose. So weight matrix and eigenvector, when they are multiplied, and now it is called as a weight. Now derived weight vector is multiplied by the diagonal matrix. And what happens there? Let us see. And D is the diagonal matrix shown above in the previous slide. And when you multiply that weight vector, as I already told, W1 to Wn, there is a dimension of the weight vector. Actually, weight being matrix, you are converting that weight matrix when multiplied with a vector, and that gets converted to a vector. And this is a weight vector, and that is multiplied by the diagonal matrix as we saw in the last slide. So what happens when a vector and matrix are again multiplied? Each ith element of Q transpose W star. So this is Q transpose W star, that is a vector. I have written here as W's. Vector is being multiplied by the ith element of the diagonal matrix, that is W1 is multiplied by lambda 1 into lambda 1 plus alpha, and Wn is multiplied by lambda n divided by lambda n into alpha. Then what happens? Let us see. So a generalized statement is given here. The ith element of the diagonal matrix is multiplied with the weight vector. So each element of the weight vector gets scaled by lambda I divided by lambda I plus alpha. So this is a very concluding statement which has to be remembered. Each element of the weight vector is multiplied by the dimensions, that particular dimensions, lambda I divided by lambda I plus alpha. So we have to analyze this lambda I divided by lambda I plus alpha. So when this lambda I is very greater, that is the eigenvector which is very greater in the sense, what happens? When the eigenvector is greater, it means it is a significant direction. So when that is multiplied, what has to be done? Then that dimension of the vector is left as it is. Why it is left as it is? If you see mathematically, then lambda I divided by lambda I plus alpha, because lambda I is very much higher, that is almost equal to 1. Here it should be replaced as approximately equal to 1. So that 1 is multiplied with the corresponding dimensions weight. So that weight is left as it is. Why? Because as the eigenvector of the Hessian matrix is larger, eigenvector of the Hessian matrix is larger, and the gradient in that direction is significant. So that weight should be left as it is. So subjectively also we have concluded, and mathematically also we have seen that weight is left unscaled because it is multiplied by 1. So coming to the opposite case, if lambda I is very less than alpha, so what that means is the eigenvector of the Hessian matrix is very lesser. So that it should be multiplied by 0. That dimension of the weight vector is multiplied by 0, as the eigenvectors of the Hessian matrix lambda is smaller. So the eigenvector is smaller. So that dimension of the weight is very insignificant, and this is called as the scaled dimension. So we have to remember, when that is multiplied with 1, that is called as the unscaled direction, and when that is multiplied by 0, that is called as the scaled direction. Why this is called as a scaled direction means, because we are multiplying by 0 and we are offsetting that weight to 0 approximately. So this is approximately equal to 1 and this is approximately equal to 0. So it is approximately brought down to 0. The insignificant directions are almost nullified. That is what is the outcome of this hyperparameter that is being added as a penalty term. And importantly, the effective parameters of the neural network should be studied. The effective parameters in the sense, what are all the entire weights in the diagonal matrix we have to see. We are having lambda I divided by lambda I plus alpha, and we claimed that several dimensions of this I from starting from 1 to n are being nullified. So some of the parameters are nullified. The capacity of the machine learning model is being reduced. So that is what the capacity have to be reduced to avoid the overfitting. That is what we started with the lecture. So here the effective parameters are being reduced. The two insignificant directions are nullified and the significant directions are left as it is. Since some dimensions become 0, the number of parameters is reduced, thereby reducing the model complexity. And that is what is simply given. And figure shows the illustration of the L2 norm penalty. between the two weights W1 and W2. We discussed about multidimensional weights. For simplicity, we are discussing with the two-dimensional weights W1 and W2. What we can infer from here is this is W star, that is the unregularized weight, and this is W cap, that is a regularized weight. So what happens here? This is the scaled dimension. The scaled dimension is pulled towards 0. So this is the direction in which the eigenvectors are very less, or these are all the insignificant directions, so those are pulled down towards to 0. Whereas the other dimension, this is a significant direction in which the eigenvectors are having significant values, it is almost multiplied by 1, so they are almost kept equal to the same value. So that is what about the L2 norm penalty, where we have reduced the capacity of the model by nullifying the weights in several dimensions, whereas maintaining the weights in certain dimensions. So thank you all.